Hello everyone, welcome to Chapter 4, Applications of Derivatives. The focus of this lecture will be related rates. And when we say related rates, there is a relation between rates of change. So we are going to find the rate of change, which is the slope or the derivative. And we use the language rate of change because we're dealing with real world or application problems. And we use rate of changes of other known information to find what is missing. So I'll say rate of change from other known rates of change. And as I've always mentioned, we will use algebra before calculus. So usually we will need algebra techniques before we could apply calculus techniques. So think of all the stuff you learned in geometry, algebra, because when it comes to real world problems, if we can visualize it and draw a diagram, usually it gives us some kind of a known shape, right? Some familiar information. So for that, geometry helps us, like similar triangles, or for geometric shapes, just finding the area, the volume, and those kind of things. And algebra, I could think of Pythagorean theorem and concepts like that. So we could use a combination of these things to find related rates. So we'll be looking at specific problems, different types, of course, to help us evaluate unknown rates of change. So I have a strategy here that we could use for related rates problems. This strategy is not anything new. You've seen this or you've been introduced to this strategy in algebra whenever you encountered word problems. So here we're being a little more specific because it's to do with the related rates, which involves calculus. So first of all, we say draw a picture and name the variables and constants. And whenever it's time that's involved in the problem, use t for it, and assume that all variables are differentiable functions of time t, because most often these are word problems that have some relation to time. Next, you write down the numerical information and of course convert it to the symbols. Like for instance, if they say the rate of change of area with respect to diameter is this, and they give that in words, you want to change it to symbols like dA over dd, like in one of the problems we did previously, so that you now have this information in the symbolic form. Third, write down what you're asked to find, and you try to express it as a derivative, because that's usually what is asked in this section, related rates. Step 4 is to write an equation that relates the variables. So you'll have known information and unknown information, and the big deal is to find the bridge that connects the known with the unknown. And for that, you may have to build a bridge brand new, meaning you'll have to build that relationship based on the problem directions or instructions. Sometimes that bridge can be built just by connecting a predetermined formula, like area of a circle would connect the area and the radius. So that's a natural predetermined formula that you can use as a bridge between area and radius. Like that, we want to look at ways in which we can make this connection. Then once you've got that, you'll have to differentiate with respect to time t, and then finally evaluate. Evaluate means to find the value. You see the word value in evaluate, so you know that you are actually trying to find the information on the missing variable, or in this case the missing rate. And let's begin with the first problem. Water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay. Now, this diagram is given to us, but usually we'll have to draw this diagram. So we always think of a cone like this, right, technically. And so when they say base radius, the cone sits down like this, otherwise it can't stand, right? But here, this is a tank, so they fitted it to stand point down, and so that's what it says, the tank stands point down. And so the base radius is now flipped, okay? So I will remove this diagram, and then we'll come back and say, okay, so because it's point down, the tank looks like this, and the the water is filling into the tank. And this green region here indicates the water quantity in it, and we can see that the green portion, that volume, is rising. It's increasing. And so we're given 5 feet to be the base radius, the radius of the conical tank, and obviously the radius happens in the circular part of the tank, of the cone. We've got that. And the height is given to be 10 feet. So that will be my height, and this will be the radius. And and as you fill your diagram with all the details, make sure that you also include the units wherever possible, so it's just easy for us to go back and reference it. And what we're saying is this, obviously the water that's filling in is going to take the shape of the cone. So the water's shape is also a cone, but the radius of this cone will be different from the 5 feet, because 5 feet is fixed because it's for the tank. But the water is increasing, which means it's varying, and therefore the radius, we usually use r for the radius. Here they're using x, which is fine. And so we mark that. And because the radius changes, now the height of the tank is also fixed, because that tank's height is not going to change, right? It's molded. It's what contains the water, so that is fixed. So that's 10 feet. However, the height of the water in the conical tank is varying because it's increasing. So the height is increasing and the radius is increasing within the tank for that water level. So this is what we are asked to understand. It says, how fast is the water level rising when the water is 6 feet deep? How fast is the water level rising? What do you think that could be? Is that the radius? Are they talking about this x, or are they talking about the y? Quite clearly, water level rising would indicate the height, isn't it? So we are asked to find dy over dt. Remember let me take you here quickly. Here it said, where was it? Yeah, the very first point it says, use t for time and assume that all variables are differentiable functions of t. So we are using that information here, and so I put the dy over dt, because it's not dy over dx. It's not about how it's changing with respect to the radius. It's how it's changing with respect to time. So this is what we need to find given. So what is the rate of change, or how fast is the water level rising when the water is 6 feet deep? That means it's given a particular instant. So given, or when, I'll just say when because I'll just use the language as in the problem. When y is 6 feet. You know, y is not going to remain at 6 feet. It's going to immediately change, right? The value will change. But at that instant, when y is 6 feet, what was or how fast was the water level rising? Okay, we get all these things. Now, I want to come back here. We used this information, we used this, and we kind of took note of this. We even took note of how fast is the water level, how fast. How fast is the language to indicate the rate of change. So we got all of that. But we didn't account for this 9 feet cubed, or cubic feet per minute. So we say water runs into the conical tank at the rate of, so let me include that as well, at the rate of. So what is given to us then? What does that information mean? So the biggest hint for us is in the units. So let me write that here. Rate of 9 feet cubed per minute, I would say, provides the hint that the volume is considered. Why the volume? Cubic feet. Cubic feet is only used for volume, not for area, not for height, isn't it? So the cubic feet, or feet cubed, the 3 dimension there, right? The power 3 indicates the 3 dimensions there. So that indicates a volume. Only volume can hold the capacity of that tank. So that the volume is considered. And when we say rate, it's change in time. How do I know it's change in time? Because it's cubic feet per minute. So it is with respect to time that it's being measured and considered, and its change in time is 9 feet cubed per minute. All this information, all this hint comes to us right from the unit here. Okay, the language rate and the unit is what really gives us that information. So for our convenience, let's say V represents the volume of water, okay? The green portion, right? It's rising. So it's a volume of water. X is the radius of water. Again, all this is to do with the green stuff, the green portion, and Y refers to the height of the water. Sometimes we can also call it the depth. So if it's used interchangeably, you know that we mean that. Now you can go back to your to other OpenStax ebooks to quickly verify the formula for shapes in terms of area, volume, and all that. So, or you could do a quick search, research, and that will give you the volume is, just say, volume of a cone is 1 by 3 pi r squared h. This is how they give us, where r is the radius of the cone and h is the height of the cone. But we are calling them x and y, so quickly replace this as v equals 1 over 3 pi x squared y. If you'd like to keep it as r squared and h, totally fine. Please go for it. Okay. Now we have v, one variable, x is another one, and y is another one. So we have three variables and just one equation. We know that from algebra, that's not possible. You want to have two variables, and then when you take the derivative and all that, we can handle it. Because, you know, if you, let me take you back here to the diagram. Once we are able to differentiate, take the derivative and all that, you know, we can actually substitute for y. So we have information on y. We don't have information on x. So our job is to rewrite this equation so that there are only two variables, the volume and the y, because we don't want the x. So that is our next focus. Rewrite the volume equation with two variables and they will be x and the y, not 3. The 3 currently are v, x, and the y. We only want the v and the y. So how do I make, or what is the relationship that I can use so that I can rewrite the x in terms of y, because that's the only other way we can do it. For that, I go back to the diagram, and instantly I can see that there are two cones that I can see, right? The red cone, which is the tank, and the green cone, which is to do with the water. And because of the concept of triangles, okay, I hope this is not too dark. It is getting too dark. So I want you to consider this triangle here. Okay. Yes, it is too dark. This big pink triangle corresponds to the red tank. Let me see if this makes any difference. And this blue triangle down here corresponds to the green tank, right? The green cone. But forget about the cone for the moment. Just look at the triangles and think geometry. What does geometry tell us? It tells us that these two triangles, from the tank and the water level, we can build two similar triangles. Okay? I can build these two similar triangles. They share the same angle, isn't it? So I want to come down here and help us to build that. So I'll use red for the tank. And we saw that the height was 10 and the radius was 5. And I'll use green for the water level. The height was y and the radius was x. So we know that from similar triangles, we can set up a proportion of their sides, okay, because of the similarity of the triangles. So we can set up a proportion with the radii and the height. So x over 5, right, this green radius over red radius will be the same as, in proportion wise, the green height over the red height. Okay, this is from similarity of triangles. You can set up proportions because that's how they are seen here, right, the similarity of triangles. So basically this x over 5 equals y over 10, and that's what we're trying to set up. Okay. Because this is getting a little messy, I am going to remove this, and we'll come over here. This relationship only involves x and y, and this is desired because we want to write x in terms of y so that we'll only have v and y in our equation. Therefore, this implies x is 5y over 10, which reduces to x equals y over 2. So basically, in this case, your radius is half the height. Okay. Now let's come back and rewrite our volume. Volume is 1 over 3 pi x squared y, isn't it? And your x squared is now replaced by y over 2. So now you got your equation in v and y. Let's simplify this. 1 over 3 pi times y cubed over 2 squared, which is 4. So volume is 1 over, I could say just pi over 12 y cubed. Okay, this is really wonderful. Now we've got this equation manageable. Now it's time for us to find the rate of change. So to find the rate of change, how do I know we should find the rate of change? First of all, if you come back here, well, it's related rates topic, so you know somewhere that's happening. But we just discussed about how the rate of 9 feet cubed per minute, that information was to do with the volume, and it was the rate of change of volume with respect to time. That's what this is. So you know you have to differentiate the volume formula. Also, we just took note here that the water level rising, dy over dt, is what we need to find. So all that setup can happen only if we took found the rate of change for this volume formula. So to find the rate of change, we need to find the derivative of v, the volume formula, with respect to time. Again, nowhere does it say explicitly with respect to time because you have the v and the y. Time is a new variable t. But again, that clue comes from both the instruction in the beginning as well as the fact that it is 9 cubic feet per minute. Per minute indicates that it's with respect to time and not with respect to some other variable. So coming down here, differentiating with respect to time. So I'll just say differentiating with respect to t because I'm introducing the variable t here. So dv over dt will be, this is a constant pi over 12 times, y is also a function of time, right? As time goes on, the volume, the height of the, y is the height of water. Height of water increases. So that's going to be 3y squared times dy over dt. Both these variables, v and y, are both functions of time. They're differentiable with respect to time. Excellent. So we got all these details. I think we can even go further and simplify this. 3, and that will be a 4. So write it one more time. dv over dt is pi over 4 y squared times dy over dt. Now we are given already that dv over dt is 9 cubic feet per minute. We don't need to write the units here. And we are told that at a particular instant, y is 6 feet, for which we need to find dy over dt. That's the missing information. So let's go ahead and plug all these in. So 9 equals pi over 4 times 6 squared times dy over dt. we have to solve for dy over dt. We'll get to that. So what I'm going to do is 9 equals pi over 4 times 36 times dy over dt. And I'm doing it very, very slowly, in the sense I don't need to show this much detail. But being the first problem, it's just like a warm-up for us. So this implies dy over dt. If you solve for it, you get 9 on the left. So you divide both sides by 9 pi, basically. So dividing both sides by 9 pi, you get 1 over pi. dy over dt is 1 over pi, but because it's a word problem, it makes a little more easier for us if we were able to round this. So this rounds to 0.32. Okay. Now again, it's still not complete because we didn't attach the units. So we always want to interpret our answers when it comes to word problems, because that's when you're actually addressing the question. The question was, how fast is the water level rising when the water is 6 feet deep? So what do we say? We say the water level is rising. It's positive, right? The dy over dt is the slope. Positive slope means it's increasing. Therefore, here it's rising. It's rising at about, I have to say about because I rounded the 1 over pi, right? 0.32 dy. Y is the height. Height is measured here in feet because we know that from cubic feet per minute. So it's feet over time. So feet over minute. So that will be 0.32 feet or foot per minute when the water is, I shouldn't say why, when the water is 6 feet deep. I'm using the sentence right from the question to interpret my answer. And this is so important because we're looking for these details. The numerical answer as well as the units that go with it. Alright? And that makes total sense for this problem. Here comes our next problem. It's about heating a plate. When a circular plate of metal is heated in an oven, we mean industrial oven, its radius increases at the rate of 0.01 centimeters per minute. At what rate is the plate's area increasing when the radius is 50 centimeters? Okay. The first thing to do, though, is to understand the problem. Okay. If you understand it, then you can visualize and then draw a diagram and then assign all the known information to it. So here's a circular plate. So you know the shape is circle. And this plate of metal, when heated, is increasing. It's expanding. So when it expands, the radius increases because it's growing. It's becoming bigger. And when it's growing, the area also grows. As the radius grows, the area grows. And that is what we're trying to talk about. So then at least we get the idea of what we're trying to draw here. So what I did here was to draw two concentric circles, basically. The red circle is the actual circular plate of metal. And this, when heated, expands and becomes the blue plate. Okay? The red plate becomes or grows into the blue plate. So to kind of illustrate that, I have the red, which has its radius. Okay? Is the radius given to us? We'll talk about that. Then we have the radius for the blue plate. Okay? So the radius from red has grown to the blue. All right. Coming back to the problem, its radius increases at the rate of 0.01 centimeters per minute. You see the clue words there, rate. Rate of what? Rate of the radius. And how do I know it's increasing? The rate is +1. Secondly, I know it's increasing with respect to time, not anything else, because it's centimeters per minute. It didn't say centimeter per feet or things like that, where they didn't correspond this increase or this rate with some other variable. It's with respect to time. All right. So then I'll come back here and quickly make a note, and I'll say radius, rate of radius with respect to time. Right? That's what I have there in English. That's how I write it in English. But then if I think of the variables, the usual variable for radius would be r, okay? This r became this. So then I will say dr, the rate means the derivative. So dr, rate with respect to time. So dr over dt, I would write it as 0.01 centimeters per minute. Okay, minute. Then I have, at what rate is the plate's area increasing when the radius is 50 centimeters? Okay, that's interesting. So then I come to this side and say, okay, this is talking about the rate of the area. And that is also changing with respect to time. With respect to time. That means I'm talking about the capital A, because area gets the capital A. dA over dt, we are asked to find that when radius r is 50 centimeters. So this is how you draw and reason out, put it in words first and then translate it. So you get an idea now. Now the big deal is, they're talking about area, they're talking about radius. Is there something that connects these two? Absolutely. That's a big deal in the formula for area of a circle. So area of a circle is pi r squared, as simple as that. So we got that. And then we just have to take the derivative. So dA, we have only two variables, so all good here. No worries like the previous problem, where we had to use similar triangles and all that to get to the other one. So dA over dt equals, pi is a constant, so doesn't get affected by the differentiation, times 2r. Remember, this is all implicit differentiation, so it's dr over dt. Implicit differentiation means that these variables a and r are not directly the ones we are differentiating. We're differentiating all of them with respect to time. So there is no t variable in the problem, but we know it's all with respect to time. Okay, we have dA over dt, that is to be found. So that's missing. Pi, 2, all these are constants. R for a certain radius, 50 centimeters. We're asked to find dA over dt, and for that time dr over dt is 0.01 centimeters per minute, of course. So we got all of these things. In fact, this is a very comfortable problem because the missing information is already on the left side. So pi times 2 times 50 times 0.01. If we do all the computation, we get pi. And because it's area over time, area is centimeter squared per minute. So you can leave it like that because it was a nice pi, or you could make it like 3.14 square centimeter per minute. Okay. So that was a nice convenient problem. We'll look at another type in the upcoming problem. Well, I included the interpretation for the previous problem. Here we go. A sliding ladder, that's the theme here. A 13-foot ladder is leaning against a house when its base starts to slide away. You can see the accompanying figure. By the time the base is 12 feet from the house, the base is moving at the rate of 5 feet per second. It's sliding down fast. Okay. In fact, they gave us this arrow here, the red arrow, to kind of show us that this base is sliding off on the ground, and so the height is dropping. How fast is the top of the ladder sliding down the wall then? B. At what rate is the area of the triangle formed by the ladder, the wall, and the ground changing then? C. At what rate is the angle theta between the ladder and the ground changing then? Okay. So this is really interesting. So we have the 13-foot ladder that's leaning against the wall, and that is sliding down. Okay, we have 3 questions here. But these details were given to us, at least, the variables are fixed for us because of the diagram. We have the x-axis and the y-axis to help us put it in perspective. So your base is x, and they put x of t. Why? Because it's with respect to time. And how do I know it's with respect to time again? You see that it's 5 feet per second. So second is the time, indicating that x is a is a function of time, and y also is a function of time. Okay. Does the ladder change? Of course not. The ladder is 13 feet. Its length is fixed. But when it slides down the wall, then its height will change, and its base from the house also will change, because it's kind of dragging down, right? It's moving. It's falling. Okay, with all these things, I also want to add these other details. It says, by the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. Okay. So to kind of put that again in perspective, you know, if if this x is changing, right, how fast it's sliding would be the rate of change of this base with respect to time. And how fast is this height falling? That'll be dy, because that's the y, with respect to time, isn't it? So this is again coming down. So we have these two details, and when we get to the specific problem, then we'll try to apply those values, the 12 and the rate of change, because the rate of change is 5 feet per second. Would that be dx over dt or dy over dt? So we'll use that when we get there. Of course, it's dx over dt. We'll get to it. Okay, so focusing on part A. Part A is, let's come back again. How fast is the top of the ladder sliding down the wall then? So what are we trying to find? We are trying to find dy over dt. Okay, put a question mark for that. What is dy over dt? So in order to get to dy over dt, we need to have an equation that has the y in it, so that when we differentiate it, we get dy over dt, isn't it? So what will be the relationship here that I can use to connect the x and the y and the ladder? Quite clearly, we can use Pythagorean theorem. Pythagorean theorem is good only for right triangles, and we know right triangles form 90 degrees, right? Only for right triangles. So clearly this forms a right triangle. So Pythagorean theorem, or Pythagorean theorem, says x squared plus y squared, right? A squared plus b squared equals c squared. Let me write the general form, where c squared is always your, c is always your hypotenuse. Hypotenuse is always the longest side of your triangle, okay? So this is one of the legs or the sides of the triangle, right? This is also one of the other ones. The legs are the shorter ones, of course. The c is always the hypotenuse. Hypotenuse is always the longest side. How do I know which one is the longest side? The longest side is always the side opposite the 90-degree angle. It's easy to find the 90-degree angle. It's where it forms this box shape, right? Where the two sides of the triangle meet at 90 degrees, or are perpendicular to each other. So the side that's opposite to the 90 degrees is always the longest side. In our case, it is our ladder. So coming back here, any one could be the x and the other one could be y. So x squared plus y squared equals 13 squared, because my c, the hypotenuse, is the ladder, and the ladder is a fixed length. So that's 13 squared. Now we're ready to take the derivative. So I'll say differentiate with respect to time t. So it's going to be 2x dx over dt, implicit differentiation again, 2y dy over dt. And this is a constant. Don't even worry about finding 13 squared, because the derivative will be a 0. Okay. We'll come back and see. Now, is there a way I can rewrite this information? Well, first of all, we know that we need to find dy over dt, isn't it? Because they said, how fast is the top of the ladder sliding down the wall? So that is dy over dt. So all that is fixed. So rewrite or solve this for dy over dt. So I'll let you do the algebra part. dy over dt, okay, subtract 2x dx over dt, and then I will divide by 2y, and the 2's will cancel off. So I'll be left with dy over dt negative x over y dx over dt. Now, do I have the details to plug in for all of these? Now, we are told outside A, B, and C, right? Outside A, B, and C, that the base is 12 feet. When the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. So I'll come over here and say this dx over dt is 5 feet per second when the base, which is the x, right, is 12 feet. It's for that instant that this works. So that's the information I'm going to use over here. So then I'm going to say, well, x will be, well, this is unknown, so that's a question mark. X is 12, and dx over dt is given to be 5. But I can't have two unknowns. What is y? Right? You can't have two unknowns. So for that, I'm going to fall back on the Pythagorean theorem. Now remember, this is for that particular instant when your base is 12. So when x is 12, right, when x is 12, x squared plus y squared equals 13 squared should give us a specific y, isn't it? So this will be 12 squared plus y squared equals 13 squared. Go ahead and solve for y. Y will be square root of 13 squared minus 12 squared, which comes out to be 5. Square root of 25, which is 5. So at that particular instant, when x is 12 feet, y will be 5 feet. So I'm going to use that information back here for dy over dt, okay, right here. So then I'll rewrite that part. Dy over dt is negative x over y dx over dt. And then I'm going to go ahead and plug in here. Negative x was 12. Y we just found it to be 5 for that 12, that instant. And dx over dt was given to be 5. If we plug all these in, you know that the 5's will cancel off. That leaves us with negative 12. Why negative 12? You can look at that and see that we use the word, or rather the question used the word sliding down. The down direction is indicated by the minus, okay, because it's falling. So the negative slope tells us it is falling. Okay. So it's beautiful how it all lines up, isn't it? So we can now say the ladder is sliding down. That's your minus, okay, in the answer. It's sliding down the wall by 12 feet per second. Notice that I use the word down, so I do not use the minus 12 in the answer part. I just said down and then just use the number 12 feet per second, because that's what is meaningful in real world. Okay, if you say minus 12 feet per second, it does not make any sense to non-math folks. So when you interpret answers, make sure that the language is also appropriate to indicate the change in direction. Now let's go to part B. These are lengthy ones, so it's going to be kind of challenging to go back and forth here, but let's see. Part B is, at what rate is the area of the triangle formed by the ladder, the wall, and the ground changing then? Ooh, what rate? Rate of the area. So right here, that for B, the focus is area. So what's the rate of area changing? If I were to rewrite this in symbols, that's dA over dt, right? That is what is missing. So now I have to find another relation from geometry We saw Pythagorean theorem gave us the relationship between the sides of the triangle. But here we're not quite particular about the sides of the triangle, we're interested in the area of the triangle. So area of a triangle, generally speaking, is half times base times height. Now thankfully, the setup of our diagram is that it gives us the base, which is the x, and the height, which will be the y, isn't it? So we can use that information to replace the formula. Area is half times x times y, base times height. Now let's go ahead and find the derivative. dA over dt is half. X and y are both differentiable with respect to time. Therefore, use the product rule and the implicit differentiation that goes with it. So u prime, let me write that out here for us. So this will be like your u and this will be your v, right? So the product rule in implicit differentiation would be u prime v plus v prime u. Let's remember that. And coming back to our step, u prime is dx over dt times y plus v prime u. And we got that. Now once again, we were told that y was 12. Was it? We got 12, right? No, x is 12. Sorry. So let's come back here. So when x is 12, we need to, well, when x is 12, we just found in part A that y was 5, isn't it? So we can use the x as 12, y as 5 information. And we also saw that for this particular instant, when dx over dt is 5, we found that dy over dt is negative 12. So we're using all the information from part A. Okay. So I'll just say from part A, okay, we know that this is missing. This will be dx over dt was given to be 5. We found y also to be 5. dy over dt, we found it to be negative 12, and x was 12. So I'm going to use all these details here. And this will be dA over dt equals half 5 times 5 plus negative 12 times 12. This is kind of convenient because dA over dt is already on the left side. So do all the computation. You can already see it's going to be a negative answer. And that comes out to be negative 59.5. And because it's area, it's feet squared or square feet per second. And that's again, because of the minus, we have to interpret it correctly when you write it. So we'll say the area of the triangle and we know the area of the triangle is formed by the ladder, wall, and ground. Is decreasing by 59.5 feet squared per second. Again, remember that decreasing is a hint for the minus. Okay, and then let's move to part C. I'll take you back here to the question. At what rate is the angle theta between the ladder and the ground changing then? So the angle is between the ladder and the ground. So here, of course, we are kind of called upon a bit of trigonometry. So trigonometry will help us to deal with that angle. So this angle theta, we want this angle to, basically the rate of the angle the rate of change of the angle would be d theta over dt. So we need to find d theta over dt. So is there any relation that we can use that will work conveniently for us? Okay. Now the angle is between the ladder and the ground. So because of that language, you can think of using the ladder and the ground. Okay. So the ladder here, so if this is the angle theta, this is the opposite side, this will be the, so I'll just say opposite side, and this will be the adjacent side, and this will be the hypotenuse. Yeah. So we can see a relationship between the angle, the hypotenuse, and the adjacent. So think of so cut over from your trigonometry. So cut over kind of helps us to see that cosine theta, right, cosine x or theta, in this case theta, is adjacent over hypotenuse. So cut over, ka is C-A-H, so cosine adjacent hypotenuse. So I'm going to use that, adjacent hypotenuse, just because they said the angle between the ladder, which is the hypotenuse, and the ground, which is my adjacent, right? But we also know that the hypotenuse is fixed to be 13 and the adjacent is nothing but your x. So there's 13 and x. We're basically looking at 13 and x. So I'm going to come down here, say, okay, we have for part C, angle between ladder and ground implies angle, I'll say theta now. I'll remove the word angle, because angle is theta, between, we saw that the ladder would be our hypotenuse and our ground would be the adjacent side. So hypotenuse and adjacent, we know that in so ka toa, ka is the winner. Okay, so we know that cosine theta is adjacent over hypotenuse. But we know that the hypotenuse is the ladder, which is 13, and the adjacent is our x, the base. So that's going to be x over 13. Very well. So we got our cosine theta. Let me write that out again. Cosine theta is x over 13, and this is what we will differentiate with respect to time t. So the derivative of cosine is negative sine theta times, remember the chain rule, so theta is d theta over dt, and it's x over 13, which is basically 1 over 13 times derivative of x, which is dx over dt. Okay, again, I insist on this because there is no t in your problem. You have to remember that all the variables are with respect to t. Alright, now we have to find d theta over dt. That information is missing for us. Okay. Do we know what sine theta is? Yes, we can find sine theta from the triangle, right? Because sine theta will be opposite over hypotenuse, so we can get those details, which is y over 13. We already can see that. And then dx over dt, this was again, before ABC were given to us, we were told that it will be 5. It's 5 feet per second. So we got all these details. Wonderful. Let's go ahead and first solve for d theta over dt. So that's just easier to have it on one side of the equation. So solve for d theta over dt. D theta over dt would be negative, I'm dividing both sides by negative sine theta, so I throw the negative on the top, negative 1 over 13 sine theta times dx over dt. If it's again too fast for you, you can always pause the video and compute it yourself. Negative 1 over 13 times, We just saw that sine theta is y over 13 times dx over dt. Now it's time for us to plug in all these values. Negative 1, in fact the 13s can cancel off. So we just have negative 1 over y, and y was for that particular instant 5 times 5. So all that cancel off, that gives us negative 1. d theta over dt. Now remember the theta is measured in radians because they didn't talk about the degrees there. So that will be radians per second. Time is measured in seconds and theta is measured in radians. So negative 1 radians or radian per second. Again, you can interpret this by going back to the problem and say the angle between the ladder and the ground decreases by 1 radians or rad per second. Once again, the decreases is supported by the minus. So that was very nice. We got to see 3 different types of approach we can give for that one particular problem. So we used Pythagorean theorem, we used the area of a triangle, and we also used trigonometry to find the angle, the rate of change of the angle. Problem, we have flying a kite. A girl flies a kite at a height of 300 feet, the wind carrying the kite horizontally away from her at a rate of 25 feet per second. How fast must she let out the string when the kite is 500 feet away from her? Here, I'm sorry, but I'm going to attempt to draw the diagram. Okay, that was a bad attempt there. Okay. Now, she is standing here. Okay, okay. Now you know how I can draw. That string and the kite that it's attached to, right, is floating there. Okay, the wind is carrying the kite horizontally away from her. Okay. So you can think of the horizontal action to it as going horizontally away from her. Okay, that way. So now that this blue piece, this length, the string, that's going to change, right? So we're going to call that, let's call that y. Now we're told that how fast must she let out the string when the kite is 500 feet away from her. Okay. So I'm going to call first these as x, y, and we know that the girl flies a kite at a height of 300 feet, so that is kind of fixed for us. So that's 300 feet. Okay. And specific information was that when her kite was carried away horizontally, it was at the rate of 25 feet per second. Okay, horizontally. So it is carried away horizontally, meaning x. So dx over dt was 25 feet per second. Okay. And then the next part is when y, this length of the string, okay, how fast must she let it out when the kite is 500 feet away from her? That means when y is 500 feet, what is dy over dt, right? The speed in which the length of the string is changing. So that is the focus here. So here again we have formed a right triangle because it's with the ground. It's going to be a right triangle. Therefore, x squared plus 300 squared, remember, it is the sum of the square of the sides. That's equal to the square of the hypotenuse. Hypotenuse here is opposite the 90-degree mark, so y will be the longest side. So x squared plus 2, 3, 4 y squared. Okay. Now take the derivative. 2x dx over dt plus 0 equals 2y dy over dt. So we have some specific information. We are told that when y is 500, that particular instant y is 500 feet, we can use x squared plus 300 squared equals 500 squared, isn't it? Because you can replace your y with 500. That will help us to find x at that specific instant. And that comes out to be 400. Okay. So x is 400 feet for that particular instant. This allows us to come back and substitute 2x dx over dt equals 2y dy over dt. And let's plug those in, for which I'm going to quickly recall that x will now be 400 dx over dt. That information was given to be 25, right? We wrote that 25 feet per, it's there in the diagram, 25 feet per second. And then y was fixed to be 500 feet. And of course dy over dt is what we need to find. So you can solve for dy over dt and then figure this out. So solve for dy over dt. 2x over 2y dx over dt. And that will be 2 times 400 over 2 times y is 500 times 25. That comes out to be 20 after you simplify it. And because it is in terms of feet, right, the string, the length of the string is feet, is measured in feet per second. dy over dt is the girl must let out the string at the speed of 20 feet per second. You can say at the speed of, or you can say at the rate of 20 feet per second. So class, as you can see, we have so many varieties of problems that we can think of. It's going to be typically, things that involve volume, volume of a cylinder, volume of a cone, and things like that. Or you saw, like in the case of Pythagorean triangle related problems, volume of a sphere or area of a circle. Sometimes they could even ask things about surface area, in which case they'll usually give that information. They'll tell you the surface area of whatever, a sphere is like 4 pi r squared. They'll give you those details in the problem if it is something that you're not immediately familiar with. But for homework's sake, you will have to do a little bit of research, go back to algebra notes or look up the ebook to obtain those formulas. So all that will be helpful in completing these problems. So I would we're kind of ending this section now, but I want you to pay attention to 2 things. One is that your answer, numerical answer, of course, comes out right with the correct unit. And secondly, to interpret your answer, particularly when there is a minus, to use the word decreasing, falling, and words like that indicate that it is substitute for minus. And of course the units are very important. If it is with respect of it is derivative of area with respect to time, you always have, say, the feet squared or inches squared. If it is volume with respect to time, it's always feet cubed or inches cubed or cubic inches per minute or per second. So these are some major clues for us to remember when we finish our problem. Okay, so thank you again, class. I hope you enjoyed this one. I will see you in the next lecture.